Yes. Hello my dear students, in the last class we have studied about the gating techniques of SCR, different turn on methods. Madam Srimati K. Prasanna, she has revealed completely about that, and today I will be speaking about different firing techniques using resistance, R firing circuit, RC firing circuit and UJT pulse trigger circuit. So, these three I am going to cover in this topic. Now, to start with, in the last class, in fact in my session, while describing about the gating requirements of SCR, you have seen this VI characteristic of SCR. In this case, as and when you increase the gate current, Ig0, Ig1, Ig2, Ig3 etc. As and when the gate current increases, your breakover voltage reduces. So, you can keep on increasing the gate current so that SCR can turn on at an early instant. So, this is the logic of starting of your SCR, turning on of your SCR in fact. Now, in this class I will be covering about these firing techniques: resistance firing, resistance capacitance firing circuit and UJT pulse trigger circuit. Now, let us take about R firing circuit. So, what are the features? See, SCR gate specification must be considered for design of trigger circuit. So, what are the specifications that are very important before you design a gate circuit? Simply it is not a simple power supply with a resistance circuit. You need to know about the levels of voltage, level of current to be applied to the gate circuit safely, so that your SCR works or turns on very safely. The two important things that I am discussing here is protect from damage due to excess voltage and current. So, what type of or what sort of protection is required, and what are the minimum gate current and voltage requirements for triggering of your SCR. So, these 2 points are very vital before you put or design your SCR in turn on position. Now, to do that you have to refer this gate characteristic circuit. So, when you look at the layer structure of your SCR, it is a PN device in which you are going to connect the gate voltage to the P layer and cathode is a N layer. Now, you can look this PN device as a PN junction diode which is forward biased. Now, we can see here these two graphs or this characteristic curve is very important to understand the gate characteristic and decide about the value of resistance, value of voltage and current etc. Now, there are two curves you can see there, this is a curve 1 and this is curve number 2. These two curves are drawn for the same SCR, they are not for different SCRs. You remember here, you can see this curve number 2 is for highest gate voltage that your SCR can accept very safely. So, this is VGM, gate maximum voltage. Now, the other curve which is drawn here, this is curve 1, this is for highest gate current or lowest value of voltage. For a low value of voltage, if you increase current, for a high value of voltage, for a less current. So, these two curves are drawn and this curve joining this is a power PGAV, average power requirement, which your gate current or voltage should lie within this area. This is the boundary, so that if it lies within this area, your SCR will turn on very safely. And there are another important thing is minimum gate current requirement, that is OX and OY. These two are the minimum levels required to turn on your SCR. And there is one more thing, that is OA, that is non triggering level. So, you must maintain minimum level of this voltage OA, so that your SCR will turn on. So, these are the requirements. So, from this very important gate characteristic curve, we can decide what is the maximum voltage, gate voltage, and what is the maximum or highest current, gate current requirement. So, these two deciding factors are very much essential before you decide or before you design a gate circuit. Now, we look this gate circuit as a PN junction diode, wherein we are going to operate it very safely. So, from this characteristic, so we can very well decide the requirements. See, these are the things. Ox is a minimum gate current requirement, Oy is a minimum gate voltage, and OA is the non-triggering level. So, if your gate current is here under this OA, if you refer the previous graph, you can say it is a non-trigger voltage. So, your gate or your SCR will never trigger if you maintain this voltage OA. So, minimum is Ox for current, Oy for voltage. Next is, this is the gate circuit design. Okay. Now, you have this anode, cathode and gate. Gate is connected to a separate DC source. Remember, it is a DC source. All are DC values. By simply applying Ohm's law, you can calculate the whatever the value of resistance required. And this is the source voltage and this is the source resistance. So, because of this EMF source, the current Ig is flowing into the gate circuit. Now, when it flows like this, so there is another resistance connected which is in parallel to the circuit between gate and cathode circuit. So, this is a protective circuit or stabilizing resistance. So, this resistance you are going to find in most of the gating circuits, which is required for a leakage path for the current. So, without which it can damage your SCR, or your gate cathode junction will be crowded with electrons and holes and it gets damaged. So, this is a damage control resistance. So, this is also an important criteria before you design a trigger circuit. Now, this is your R firing circuit. So, this circuit you have to explain. So, why there are three resistances, you can see there the resistance R1, variable resistance R2, you have a diode and you have another resistance, and in between there is a connection to the gate. So, why this circuit? This you have to understand very carefully. Otherwise, you would have straight away connected a resistance here in this path, so that you could have triggered this circuit. I think just now I told you about the significance of this resistance, resistance R. This is a stabilizing resistance, okay, which prevents or which carries the leakage path current. And now, there is a variable resistance here and another fixed resistance here. Why these two resistances? Yes, this is a variable resistance. If you make this 0 without the presence of this resistance R1, so there is all possibility that a very large current can flow into this path, and definitely it will damage your SCR. So, this R1 is another safer value resistance connected in series with the variable potentiometer R2. So, which prevents the heavy inrush current to the gate circuit. So, like this the SCR needs a protection, it is not mere connecting the bias to this SCR gate and cathode circuit. And now, this is Vg gate voltage, which is required, minimum required gate voltage to turn on your SCR. Now, this is a R firing circuit. So, this is all about the explanation of this circuit diagram in fact, and you can see here it is a sinusoidal voltage Vm sin omega t, you are applying the sine wave here, source voltage. Now, to understand this, so now when you say firing, so your SCR starts or gating requirements are like this. In fact, resistance R1 is connected in series with R2, this is to limit the gate current as I have already told you, and this is, if R2 is made 0, this should not damage SCR. So, R is a stabilizing resistance. Now, maximum voltage drop across R should not exceed VGM. Maximum voltage drop across R means this one. So, this should not exceed maximum gate voltage. So, this has been obtained from gate current characteristic graph just now I had discussed. Now, this is the one. Now, you can see the diode connected in series with the circuit. This diode is a half wave rectifier which allows only positive half cycles. Positive half cycles. The amplitude of this can be easily varied by resistance R2. It is a potentiometer. So, Vg is a gate voltage, it is in phase with the supply voltage. Since it is a resistive circuit, it is very well known that voltage and current are in phase in case of this resistive circuit. Now, these two parameters, gate voltage as well as supply voltage, they are in phase. So, increasing Vg above Vgt, this is gate turn on voltage, turns on SCR at firing angle less than 90 degree. Why only 90 degree? This you have to understand properly, because it is a R firing circuit, and we say the feature of this R firing circuit is it fires the SCR up to 90 degree. The maximum firing angle is only 90 degree. Now, we can see, you can understand this concept from this graph. So, the analysis of this R firing circuit, definitely waveforms are very much essential. So, you have to write down the waveforms whenever you explain these firing circuits. So, which is significant here, and you can easily understand what is happening here. You can see the first waveform, this one is an input voltage waveform representing Vm sin omega t. It is a sine wave, clear sine wave, you can see there. In the next one, this is Vg, this is gate voltage. Gate voltage, it is here, we have shown only half cycles, the negative cycles are suppressed, because this is coming through a diode. You refer the diagram. Okay. If you refer the diagram, you can see the diode connected in series with the circuit. So, this diode allow only positive half cycles. So, that is why only half cycles are shown here, negative cycles are suppressed. Now, the another line, dotted line, you can see, that is VGT, gate trigger voltage. Now, in the next line you can see this is V naught, no waveform is shown here, it is 0. So, that means SCR will never turn on, because your requirement is not yet met with. That means, the peak voltage is less than VGT. In this case, your SCR will never turn on. You can see V naught is also 0, I naught is also 0. So, this is a thyristor voltage available across. Now, this is the one which shows there is a minimum requirement to turn on your SCR. Now, we can see here in this graph, once again this is your input sine wave form. When you make gate peak voltage is equal to gate trigger voltage, then your SCR will turn on. So, it turns on, and your firing angle here it is shown, it is exactly 90 degree. If this VGP peak voltage is equal to gate trigger voltage, your SCR will turn on exactly at 90 degree. Now, in this you have seen the output voltage V naught shown, okay, V naught shown for an alpha 90 degree here, I naught is also shown here, and thyristor voltage is also shown here. But while explaining, this is enough. So, in the examination you can write explain R firing circuit, means you can stick on to only these two voltage levels to define or explain this resistance firing circuit. So, when gate peak voltage is equal to gate trigger voltage, your SCR will turn on exactly at 90 degree. Then how to turn it on below 90 degree? Yes, there is an answer here. You can see this gate peak voltage, if you increase beyond VGT, your SCR turns on at less firing angle alpha You can see here this is a voltage V naught which has been turned on here. Okay, this is the output voltage V naught and I naught. Once again, you need not write V naught, I naught, you can express only V naught, that is enough, because it is a trigger angle. So, voltage and current are in phase since it is a resistive circuit. So, you should remember these things very carefully, and you need not write this Vt also. This is the voltage across thyristor. If you connect this to a CRO across this thyristor, so you are going to get this type of waveform, which is not important for us now. So, you have to understand only when you fire your SCR using resistive network or R network, the alpha, firing angle alpha varies from 0 to maximum 90 degree. So, this is very clear from these two waveforms. So, this is alpha less than 90 degree. Now, this is the maximum angle of firing, maximum gate voltage obtained by R firing. Now, this is the actual practical circuit diagram given for you. You can write or you can try this in your laboratory wherein you have 2P4M SCR connected through a diode with a 1 mega ohm resistance. This is a variable resistance, and this is 10K half watt resistance, and this is 4.7K 10 watt resistance connected to a CRO with a transformer 909 transformer. So, it is a step down transformer. So, you can rig up this circuit in the laboratory. You can always test this connecting a CRO. You can obtain this type of waveforms, and you can very well appreciate the theory behind this, that is about resistance firing circuit. Now, what are the features of R firing? So, looking into these things, it is the simplest and most economical method of firing circuit. Of course, this is not all it is not in industrial use in fact, but still it is a basic thing to understand the firing techniques or gating of your thyristors. Limited range of firing angle between 0 and 90 degree. With respect to resistance firing, the angle of firing is limited to 90 degree. Dependent on temperature, yes, because it is a resistance, whenever current flows through the resistance, temperature increases, and the variation in temperature causes variation in triggering also. So, these things are to be kept in mind before you use this resistance firing circuits. Then you can see another important one, difference in performance between individual SCRs. So, it will not be same, you have to design a separate circuit and separate values for different SCRs based on their requirement. So, this is all about resistance firing circuit. Now, the firing angle is a restriction here, up to 90 degree you can fire your SCR. But what to do in order to increase this firing angle beyond 90 degree? Yes, there is another circuit, that is RC firing circuit. So, this is an RC triggering circuit, resistance capacitance triggering circuit. So, when you connect resistance and capacitance, so it is a timing device we can say. So, the product of R into C is time, it is a time dependent. So, charge capacitance will charge and discharge. So, this charge and discharge time is a product of R into C. So, this RC triggering circuit will increase the firing angle by transferring or by shifting the voltage levels. So, this is the actual circuit that is expected from your side for an RC firing circuit. You can see the load here, you can see the variable resistance here, and you can see the capacitance here, and there are two diodes D1 and D2 connected. Yes, this is another requirement for a diode, this D1 and D2, they are protective devices also, because during negative cycle they will get, or there is a possibility of damage to gate. So, this is very much required. Now, this is an RC firing circuit. This diode D1 prevents breakdown of cathode gate junction through D2 during negative cycles. So, this diode D1 is a protective device. You can connect this diode in parallel also in some circuits. You can find this type of connections in gating circuits, diode being connected in series, diode being connected in parallel. So, what is the significance? When you connect them in series, it reduces the current. When you connect them in parallel, it prevents the voltage, high voltages. So, these are all protective devices. You have to understand each and every component connected in the circuit before what they do in the circuit, because each and every component they have their own significance, and that is why you have to analyze the circuit and then understand properly, so that it will give you a full meaning about these firing circuits. Now, during conduction of SCR, capacitor keeps on charging. See, these points you have to follow it very carefully if you want to understand RC firing circuit. So, during conduction of SCR, capacitor keeps on discharging in positive cycle. During negative cycle, capacitor keeps on charging. So, SCR triggers when capacitor charges to a voltage equal to VGT. So, these are the important points to understand how this SCR RC circuit behaves. Now, this is a waveform. Once again, the analysis of waveform is very important to understand how this alpha firing angle can be extended beyond 90 degree. Now, you analyze this circuit. When you come back to this circuit, you can see this is the input is the AC sine wave form, which is applied to your capacitor. Now, analyze this waveform. This is quite important. You can see this is a negative peak, which is applied across your capacitor. Capacitor charges to this peak value. Then you follow this. This is Vm. This is the input voltage, Vm sin omega t, input source voltage. So, this is sine waveform. Now, this Vm is negative peak here. Now, Vm is decreasing, input voltage is decreasing and reaching 0. You see the capacitor here. So, this capacitor will come and stay somewhere here, OA. This is the voltage of capacitor. It reduces to some extent. When the input voltage crosses this junction 0, now capacitor, observe the capacitor, it has started discharging. This is the line of discharge. So, it discharges. When this discharge voltage is equal to Vt, then only your SCR will trigger. This concept is already explained in R firing circuit. So, the capacitor voltage should equal the gate triggering voltage, then only your SCR will trigger. You can see this alpha shown here. Okay. Now, this concept you have to write very properly. Now, this capacitor charges to a peak value during negative cycles of input. When the input starts changing, so this is the input reaches 0, your capacitor slightly reduces from the peak value, and when input voltage goes positive, your capacitor starts discharging. Then when this voltage Vc, that is capacitor voltage, equal to Vgt, it will fire. So, this is the concept. Now, this graph or this waveform is shown for alpha less than 90 degree. Now, Rc is the product of R into C is a time constant. So, you can decide these two values of resistance and capacitance to give triggering time, charging time. R into C, the product of resistance into capacitance, is charging time. Now, this is alpha less than 90 degree. Now, our intention is you have to fire this SCR beyond 90 degree. Of course, this terminal thyristor voltage you need not write. You write only this one and this one. These two are sufficient to explain the contents. So, this is for alpha less than 90 degree. If you want to increase the firing angle, what to do? Yes, you vary the resistance. Resistance is there. Say this is This graph is for low value of resistance. This waveform is shown for low value of resistance. When resistance is less, current is more, capacitor charging voltage is less, so it fires at this angle. If you increase the value of resistance, high value of resistance, current is less, it takes long time to discharge, time of discharge is more, because R into C is a time constant. So, a similar thing happens here, once again during the negative cycles of the input, the capacitor charges to the peak value. So, when the input crosses this 0 or reaches 0, the capacitor voltage slightly reduces, and when the input voltage goes in positive direction, your capacitor starts discharging. So, this is the discharge path, it has taken a long path, and until it reaches VGT, your SCR will never fire. You can see here it has crossed the peak value 90 degree here, it has crossed the peak value. Now, you can fire this SCR beyond 90 degree. So, this waveform is very important for you, so that this shows clearly that your firing angle has increased beyond 90 degree, and even 0 to 180 degree can be obtained. So, complete firing circuit is this one for RC firing circuit. What is it? Next, that is the half wave trigger circuit, because you have connected a diode in series with it, it will allow only positive cycles. RC full wave trigger circuit is this. In this case, input itself is rectified and then supplied to load, connected to RC circuit, and this is the waveforms for low value of resistance to trigger the SCR below 90 degree, alpha less than 90 degree. You can see both cycles are available, you can see the waveforms on both cycles. So, firing angle alpha less than 90 degree. So, you can leave out this one, voltage across thyristor, you can omit this part, you have to write this and this is important. So, this is for low value of resistance. So, to increase the value of resistance, fine, it will go beyond this 90 degree, you can show the waveform of this and this is for a full wave RC trigger circuit. Now, this is all about resistance and resistance capacitance triggering circuits. So, this is very important concept to understand the resistance firing and RC firing. So, in case of resistance firing, you have seen that the triggering voltage is only 90 degree, maximum triggering angle is 90 degree, and voltage and current are in phase the circuit. Whereas, an RC circuit, you can obtain firing of SCR then this is the practical circuit, in which you have a transformer 909 transformer, and this is the capacitor, and this is a diode, okay, it is a protective diode, and then this is the actual practical circuit. So, if it is not visible, I will tell you the values, So, this is the transformer 909 transformer. So, diode D2 1N4007, this is also 1N4007, capacitor is 0.1 microfarad, and this is a 1 mega ohm resistance, this is 10 k ohm resistance half watt, and this is 4.7 k ohm 10 watt, and this is a 2P4M SCR. So, you can try this if you have a kit. So, no need to rig up in your colleges. So, if you do not have, if you connect them in discrete format, so using a breadboard, definitely this can be, you can try this circuit, so that you will obtain or you will appreciate the value, the firing angles of R and RC circuits. So, this is actual practical circuit. Now, there are problems with RC circuit, because you have lot of heating taking place inside, and it is in fact it can damage your SCR and not popularly used. And now, the next topic is SCR being fired by UJT. UJT is a unijunction transistor. Now, this is a transistor, unijunction transistor. So, this is 2N2646, this is a unijunction transistor, and this is how to identify the terminals of UJT. Of course, all these things I have already taught in your electronics 1 and electronics 2, but still I am just brushing up your memories, So, this is your UJT, and you have a base emitter B1 and B2. Okay. So, this is the identification, terminal identification. Now, this is a little bit theory about this UJT, you can say. So, it has a N layer in which p type semiconductor heavily doped is diffused into this area. You can see the distance between B1 and emitter, B2 and emitter. So, distance is more, resistance is more, distance is less, resistance is less. Now, we can see this is a junction PN, this forms your diode. So, you can simply write the equivalent circuit of this UJT. Okay. So, equivalent circuit of UJT is this one, you can see here. So, PN junction is represented by a diode, and you have resistances RB1 and RB2. RB1 is shown as variable, RB2 is shown as fixed. So, this is the resistance between emitter and B2, and this is the resistance between emitter and B1. Emitter B1 resistance, because the path is large, so it acts as a variable resistance, it is a pure resistance like this. Now, this is the equivalent circuit of this UJT, and now you have to understand the characteristics of UJT, VI characteristic of UJT. So, when you maintain the bias like this, so this is the circuit. So, this is V input circuit, input voltage. When you apply it to this diode has a barrier potential definitely. So, this will not allow the current to flow through, only leakage current will flow. You can see here, this is the region where your UJT is not conducting, UJT is not conducting. So, this is in cutoff region. Now, when it reaches the peak value Vp, this is the peak voltage at which your PN junction say depletion layer, so this is being forward biased. So, this will start conducting. So, when it reaches peak value, now the curve is shown down gradient like this. So, it is going down like this. So, this is a negative resistance region, mean to say the resistance reduces, current increases. You can see the increase in current, this is the current axis, and this is the voltage axis. Now, the current is increasing, correct, and this the voltage is decreasing. So, now a point is reached where it stops here, there is a valley point. So, these are the nomenclatures used to understand the concept of this UJT. When UJT reaches this, we say it has reached saturation. So, if you will be operating your UJT in this region, negative resistance region. Now, why UJT? It is a very efficient device for triggering your SCR. Then what is the advantage of this over your conventional R and RC firing? So, this produces gating pulses, constant repetitive pulses are produced. So, this UJT is an efficient device to trigger your SCR or turn on your SCR. Now, this is all about simple VI characteristic. So, these things I have already studied. I am just brushing up, I told you, you need not study all these things for examination point of view. So, this is just to understand the UJT characteristics and why UJT is preferred over here. Okay. Now, this is an UJT which acts as an oscillator which produces continuous waveforms like this. Now, this is the symbol for UJT, and you have B1, B2 and emitter, and you can see this resistance R and C. So, this is responsible for the frequency of operation, the oscillations that are produced by UJT is governed by or decided by these two values R and C, and there is a resistance R1 connected here. So, this is the output load circuit. Now, the pulses are, you can see the pulses here, they are available like this. Now, the capacitor charge and discharge like this. So, whenever it reaches peak point, it will keep charging. So, this pumps the voltage here and this SUJT will start conducting here, and discharge path is like this. This is a discharge path. So, these are the pulses generated by your UJT. So, that is why the pulse triggering is employed here for firing or turning on of your SCR. Now, this UJT will act as an oscillator. The frequency of oscillations are determined by these two values R and C network, and this is voltage VE, emitter voltage. You can see this graph. So, that is why this is VE, and when it reaches VP, so definitely your UJT starts conducting. Now, these are the pulses. Now, here you have to understand many things here. So, this is a waveform drawn, the VI characteristic of this UJT, and this is an important thing here. Now, there are many lines you can see there. It is not follow these things very carefully, so that it will become easy for you to understand how this UJT is used as a pulse generator. Now, we can see this is a peak voltage VP, then this is VBB, maximum voltage applied, and this line, if you will draw a line between voltage x axis and y axis being voltage and current respectively, any line which is drawn here is a resistive line. So, you should be very clear here. When I draw x axis and y axis, okay, voltage and current, any line which is drawn in this area is a resistive line. Now, a line is drawn here, this is R1, that is load line. What is this R1? This is R1. Okay. So, this R1, this is a load line drawn here, R1 load line, you can see that it is drawn between this peak and this one. Now, this voltage, that is from VP and this intersecting point x, this decides the amplitude of the pulse. These are the repetitive pulses obtained at the output side, and this is decided by this value of R1. When you go on varying this, so this, when it reaches value point, so this voltage, it stops conducting, right. So, this is the one. So, it reaches this peak and goes off. So, these are the pulses generated by this UJT. So, UJT is acting as a variable resistance, that is, this value, this area is very important for an UJT to produce this kind of repetitive pulses. Okay. So, the frequency is decided between these two and the magnitude is decided here. So, this graph, this clearly shows how the variation of this load line, it is a very clear line here. So, this is a valley point and this is a peak point. You can see this is a line R, this is the R load line resistance. This, what is this R? This R is this one, this is the R. So, this line is drawn for this one, this is the negative resistance region which decides the peak value of pulse. Now, after getting these ideas, so UJT can definitely be used advantageously to trigger your SCR. So, resistance R1 should be sufficiently small, so that normal leakage current across R1 should not trigger SCR. So, these are the important things that one should keep in mind before designing the circuit for UJT. The value of R determines UJT to act as an oscillator, as I already told you. So, how to decide this R maximum value or minimum value? So, the equations are shown here. Of course, the equations are not important for you. So, in order to understand or in order to obtain the importance of these values of resistance and how to calculate the resistance, etc. So, one should have this knowledge. So, it is only a simple Ohm's law, using this Ohm's law you can simply obtain this kind of values. So, you can easily understand here, you can VBB minus VP by IP. So, this is a triangle, you can obtain this triangle, this simply an Ohm's law, VBB minus VP by IP. So, maximum peak voltage. Okay. So, this will give you the maximum value of resistance and minimum value of resistance. So, this is the equation. So, it is only by Ohm's law, you simply you can remember these things from the graph VBB minus VV by IV. So, this is valley current. So, this will decide the maximum and minimum values of R. So, value of R determines UJT to act as an oscillator. If you do not design this value or if you do not use the correct value of resistance, your UJT will never act as an oscillator and you will have trouble in producing these oscillations. So, before you study any circuit, so you must know the significance of each and every component used and why it is used. So, for a diploma holder, so we say we usually directly give the values and ask them to rig up and obtain the output, that is all. But still you should know whenever you study the theory regarding UJT triggering and all. So, one should know how to obtain this kind of values. So, simply mugging up will not help you. So, you should know the significance and importance of these values. Now, this is the circuit. Sharp repetitive pulses are produced here. So, this is the where you are going to produce a pulse and this is one more protective resistor connected here and this is the capacitor charging and discharging shown continuously here and these are the repetitive pulses. This is one simple circuit. You can see this is a generating UJT pulse. Using this circuit you can generate the pulses, required pulses for UJT. And if you are not able to see, I will tell you the values. So, this is a bridge rectifier constructed using 1N4007 and this is 220 ohm 5 watt resistor and this is BZ18. So, this is a Zener diode, this will clip the voltage in fact, and UJT 2N2646, this is the resistance 1 kilo ohm half watt, this is 3.3 K and this is 100 K resistor and this is 0.1 microfarad. So, this circuit will generate UJT pulse and this is the circuit. So, this you have to write to explain UJT firing, SCR firing using UJT pulses. So, you can see this is a rectifier, full wave rectifier connected and then this is a Zener diode. This will clip the voltage so that it maintains constant voltage across this circuit, RC circuit. Now, this capacitor whenever it charges maximum, it will make this UJT to conduct and now the output is connected to a pulse transformer. So, there are two gating circuits here. This is the advantage. This is the advantage of using a pulse transformer. What is a pulse transformer? It is a 1:1 ratio transformer. So, you can use the same circuit to trigger more than one SCR. So, there is another advantage of firing this SCR using UJT pulses. Then you can see the description given here. The diodes D1 to D4 converts AC to DC. R1, the resistor reduces voltage to a suitable value for Zener and UJT. When voltage VC reaches threshold voltage of UJT, breaks down. So, you know the threshold voltage of UJT, that means the junction point of PN of UJT, it has to reach the threshold voltage, that is peak point. The capacitor discharges through the pulse transformer, produces required pulse to trigger the SCR. So, these are the descriptions given to understand the concept of UJT firing. Of course, this is the practical circuit which is drawn for you to understand how to rig up this circuit. You can see this BZ18, this Zener diode, and now this is a capacitor 0.01 microfarad, and this is being a pulse transformer connected to 2P4M SCR for firing and this is the lamp circuit. Okay, this is the lamp single phase, and this 12012 transformer. There are two transformers used here. So, this is the practical circuit. Then why use a pulse transformer? Why this gating pulses? How it is how you can rely on this type of firing circuits? You know, the transformer, pulse transformer, it is suitable to inject large charge into the gate circuit for reliable turn on. So, this is a pulse firing. Now, a large repetitive pulses. Pulsing is suddenly you apply this maximum voltage across this particular gate and cathode terminal. So, this is a reliable method so that you can inject the current into this junction. So, it is just like in a medical field, you say taking tablet and taking injection. So, injections they are directly injected into the veins and they act very fast. So, in such case, these things, it is just like an injection. You are injecting a large charge into the gate by applying a large repetitive pulse. So, that is an advantage. So, that the pulse duration is small, so less gate power loss. Gate power loss, see if you refer the R firing and RC firing, so the gate power VGP which plays an important role, so which can damage your SCR also. So, that is why since the pulse duration is very small, the gate power loss is also less. So, no significant heating at the gate circuit. So, when the current is less, definitely your gate will not get more heat. So, heating requirement is reduced. If you use RC circuit, the heat produced is more, you have to have a lot of protection, heating protection for that. Whereas, here for a gating circuit using pulses, so it is a short duration pulse, the amount of heat produced is also less. And one more important thing that is obtained or extended by this UJT circuit is using pulse transformer. In fact, a pulse transformer acts as a good isolation from power circuit and trigger circuit. It will literally separate the power circuit and the trigger circuit. So, that is why this separation or isolation is very important concept. So, for isolating this circuit, this type of pulse transformers triggering is essential. And one more thing, that is we can trigger more than one SCR from the same pulse transformer. This is another great advantage. It is not available in your R and RC circuits. So, you can trigger more than one SCR from the same pulse transformer. So, this is an important concept of turning on of this thyristors. And of course, this is a pulse obtained from a circuit, UJT pulse firing circuit. Now, with all these, so you have seen about the resistance firing circuit, RC firing circuit and UJT firing circuit. So, in this class, in fact, the resistance firing circuit, as you have seen the graphs depicting the firing angle alpha is restricted, and it is restricted to 90 degrees. And you know why it is exactly at 90 degree. With respect to R circuit, the firing angle alpha has a restriction, it is exactly at 90 degree. So, in order to increase the firing angle alpha beyond 90 degree, so you have to rely on RC circuit. So, this RC circuit, the capacitor plays an important role in extending the firing angle alpha. Now, the charging and discharging of capacitor will extend the firing angle beyond 90 degree. So, that is an RC circuit. And next is the UJT firing circuit. pulse triggering circuit. So, you have to generate sharp repetitive pulses using UJT technique. So, UJT produces sharp repetitive pulses on a proper design, and this UJT pulses are injected into the gate cathode circuit of your SCR to turn on immediately. So, this is an advantage over the other two forms, which reduces the gate losses and increases the efficiency of your SCR, and once again it reduces heat loss also. So, unlike the other two circuits, R and RC circuits, you have enormous heat being produced because of the presence of resistance. So, now the resistance is a culprit there in fact, but we can't say without this we can't trigger the thyristors or SCRs. So, you have to arrive at a compromise, so that you have to design the circuit properly, so that it should exactly match your requirements. So, that is why before designing any circuit, you must go through the data sheets of that particular component, decide about the values of resistance required, and then you can easily use them in the circuit, so that your SCR is safe in operation. So, in all the classes, whenever we say SCR, you have to trigger this SCR safely like this. You have drawn VI characteristic of SCR, you know the breakdown voltage of SCR during forward bias, and during reverse bias the breakdown voltage of SCR, and regarding the gating requirements. So, whenever you go on increasing the gate current, your breakdown voltage reduces, SCR turns on at an early stage. All these things are true, but each and every concept, they have limitations. So, you must understand those limitations, and you must clearly explain the concept behind it. So, this is an important aspect for an electronics engineer, so that you can easily understand the concepts. So, before you start reading about these firing circuits, you must have the knowledge, thorough knowledge of these things. So, about triggering requirements, voltage current requirements, maximum voltages allowable, minimum voltage requirements, and non-triggering voltage levels wherein you cannot trigger the SCR. So, for triggering SCR you must maintain minimum latching current, latching current, holding current I have explained in the first class itself. So, without latching current, minimum latching current is required to turn on your SCR. So, you have to maintain all these aspects and then design the circuit, rig up these circuits and enjoy the firing things. You can fire your SCR at different angles. And so, I hope you have understood thoroughly about this firing circuits of our RC and UJT firing. I hope you conduct these experiments in the laboratory and enjoy these different firing techniques. Okay, thank you. In the next class, you will learn about digital firing circuit, and which is a very interesting concept of digital firing circuit. I think tomorrow you have this session of digital firing circuit, and then you will be learning about commutation also. So, what is commutation, etc. So, all those things you learn in the next class. Thank you.